Patron talk. We are absolutely delighted to welcome back Professor Anne-Marie Trio, who's going to give a talk this year about HotJupiters. In the past, Anne-Marie has spoken to us about the TRAPPIST-1 system, a system that he helped co-discover, and has also talked to us about circumbinary planets. Once again, thank you very much to Dr. Trio for volunteering to do this. We are really looking forward to this talk. I will pass you over to him. Here we go.
Hey, thanks, Luke. Thank you everyone for tuning in. It's nice that you keep your interest in science despite the circumstances and take some time to listen to talks to further your interest in astronomy. So the first thing I'll show today before I actually even start the talk is a little advert. This is mostly directed to the year 2 students. So there is a studentship program, the Isaac Newton group of telescopes. There's one also, the Nordic optical telescopes. Both of them are in La Palma, in the Canary Islands. Deadlines for applying to these studentships is in October. And so if you would like to do to spend a year working at a telescope, assisting astronomers like myself, etc., I encourage you to just take a picture of the screen, go to the website, find out when you need to apply. So it will typically be before October next year. And then if you're accepted into the program, then you can ask for a sort of a gap year or leave of absence of a year. And then you would live on that island, working by night, manning the telescope that you see here on the screen. So I encourage you to do that. It's fun. I've met several people that have been students at that telescope and that now are researchers. So I think for students that are in 3rd year right now, it's a bit late. So please, for the 2nd years, keep that information. I'll try to send that again at the end of the year as well, of this academic year. So let's start. So whoops, what just happened here? There we are. So what we'll talk about today are HotJupiters, and it's too bad that we're not in a room directly in front of each other, because then I would ask whether people know what those strange beasts are. HotJupiters is the story of the first planets that were detected outside the solar system, the first planets around sun-like stars. And they've shaped almost everything that happens in exoplanets at the moment, because they were the first found. They were the most numerous for many years. So a lot of attention has been spent on trying to understand them and trying to find out whether they are normal or whether they're abnormal. And we'll see that actually they're not very normal, but they're frequent enough to be worthy of attention. And certainly it's on those planets that we are now tuning all our methods of detection, but also the methods of characterization, for instance, trying to characterize the atmospheric composition of those planets. So let's go and find out, why HotJupiters are important. So the first thing that I think is relevant is that it's how we detect exoplanets. So the easiest way to detect a planet is really by doing some what we call direct imaging. It's like you try to do like you would from Earth. Try to look at Venus or Mars or Jupiter, Saturn. Those are bright dots of light in the night sky that move. So one could try to do that. That's what we call direct imaging. However, if you make a star the equivalent of a lighthouse, the reflected light from a planet is the equivalent of having one of these little bugs right next to the lighthouse. So it makes it very difficult to detect. So one way to do this is to try to extinguish this lighthouse using very clever processing techniques, but it's very difficult. And so for the longest of time, this method was not thought to be possible. We have ways now of solving this a little bit, but it remains a very difficult enterprise. And so most of the methods had to be indirect. And I think that's important when we're talking about exoplanets, to understand that everything that we do is inferring what's there. We don't have a direct measurement of what we're looking at. And by and large, everything that we do is trying to manipulate a little bit of starlight. And out of that, we pick out information that the planet is there and pick out what the atmospheric composition is made of, which is, I think, remarkable when one thinks about this. In fact, actually, I think someone had calculated, I can't remember the number exactly, but astronomers, ever since Galileo made the first telescope, have collected less light than would be emitted by a 100 watts bulb for a minute. So like you see, like we're working with very, very little light and yet gather a lot of information thanks to it. So let's go and look at indirect methods. Well, the main methods and first methods that was deployed, the one that led to the Nobel Prize in Physics last year in 2019, was the radial velocity method. And the radial velocity method, we effectively destroy the light that comes from the star to reveal it into its color component, its wavelengths. And that's a spectrum of the sun. So you can see here, effectively a spectrograph acts like a telescope that will look at this pattern and hence, get a higher resolution than the real rainbow. And what you see is this sort of things. So you see red wavelength, blue wavelength, and we see lots of these dark bands. Each of them corresponds to atoms that are within the atmosphere of the star, and those atoms absorb light at very particular wavelengths, and it acts like a fingerprint. It tells us what kind of star this is, and from this we can get a guess of the mass of the star. But importantly, this sort of pattern, or rather the location of very specific bands, like for instance, I'm going to look at this one here, which is the sodium doublet. This sort of bands here are always at the same wavelength, wherever you are in the universe. The only difference in wavelengths that you might see is due to the velocity of the star, and that's how we will detect a planet. So all of that, you see like it gets dark because there's less light. All of these very fine lines here tells you about what kind of star. So here is like you have several spectral types, so K dwarfs and M dwarfs, and you can see very subtle differences. You can see all those bands here have disappeared in the M dwarf, which is cooler, and therefore it's not hot enough to excite certain electron bands around each of the atoms, and therefore they don't absorb the light anymore. And that's how that fingerprint helps us find out what kind of stars we have. So now we look at this pattern here. You see it replicated underneath here. And if that source of light has this sort of spectrum, if there is a planet or anything, a star, anything that it does not emit any light, that orbits around that source of light, and then you will see the source of light vary back and forth as the Doppler effect. So this is the light Doppler effect. It's similar to the sound Doppler effect. And the velocity that we're measuring, or trying to measure or to get an idea, is of order several, tens of centimeters to tens of meters per second. So this is very small. 10 meters per second is about the speed of a sprint at the Olympics, at the 100-meter sprint. And while 9 centimeters per second is much slower than the speed at which someone walks. And right now, the best instruments have like an accuracy of about 20 centimeters per second. Actually, in work that we did with one of my grad students, just now we were looking at signals that were of that order of 20 centimeters per second, which is remarkable. It means that if you were somewhere in the universe with a torch bright enough to be seen from Earth and walking, we would be able to detect your velocity. And I think that's quite an achievement. So thanks to this method, we can measure mass. So here is the typical diagram that we show, which has mass here in units of Jupiter. You see 1 here, periods in units of years. Earth is below the graph, and you see here Jupiter, Uranus, Jupiter, Saturn, Uranus, and Neptune. And the first planet that was detected, so by and large, we were expecting planets to be in this area. The reason is that at about 2 to 3 astronomical units here, there is a line that we call the ice line. That's the line where if in a protoplanetary disk, so you have to imagine you have a star And around the star, you have a disk on which planets will form. And in the inner part of the disk, water is in a vapor form because it's too hot for the water to condensate into ice. In the outer part of the disk, it's too cold for vapor to exist. So water is in the form of ice, of building blocks. And it means that on the outer part of the system, you have more material to make a planet. Whereas in the inner part, you don't have many building blocks. You have lots of gas, but not much building blocks. So it's easier to form a big planet further out. And the idea was that because in a solar system, we have 4 big giants outside and 4 small planets inside, that this was due to this ice line. And so everybody was expecting planets to be on about 10-year orbital timescale. And so most programs that were trying to find planets were collecting data and just waiting until several years had passed to analyze those data. At the time, also 25 years ago, it was difficult to analyze these data. The computers were not anywhere near as performant as now, and to achieve very high accuracy on the velocity on the spectrum required a lot of computing power at the time. And so it was a bit of a surprise when, in 1995, 51 Pegasi b was detected exactly where no one expected it to be. We were not expecting any planets in that area. Interestingly, the teams that had been observing for decades then looked back at the data, and then they suddenly realized that they had several other planets that were on short orbits. And that's the reason why I didn't get the prize in the end, is because although they were collecting measurements, they were sort of caught in their old-fashioned idea that planets could only be beyond, or gas giants planets could only be beyond this ice line and not within. So that was the first case of a hot Jupiter. The reason being that it has a mass roughly that of Jupiter, but it's very close to the star. To give you an impression, Mercury would be at about 0.1, in terms of year, it would be around here. So this is much closer to the star than Mercury is, so a bit of a surprise. And then as we detected more planets, you can see that pretty much everything that we've discovered is within the ice line, which became a bit of a surprise, and is still the scene of some debate as to what are all these planets doing where we don't expect them to. And there's a lot of work going on there. I won't go into those details. If you want to know more, I encourage you to take my year 3, year 4 class in semester 2. So you can see here the hot Jupiters. So typically there'll be about 1 Jupiter mass, but you can see it ranges to as high as about 10, 20 Jupiter masses. The lower limit is about 1/10 of a Jupiter mass, so roughly this area. And the outer period to be classified as a hot Jupiter is between 7 to 10 days. It depends on who you're talking to. So it looks like there are plenty of them here, but in fact, there are not that many of them. About only 1 star, like the Sun in 200, has a hot Jupiter, so they're fairly rare, but they're easy to find, and that's why we see so many of them. So as soon as we knew that planets could exist here, then people thought, okay, well, let's do the transit method. Transit method where a planet will pass in front of the star. So here is a footage of the Sun. You can see here a planet Venus passing in front of the Sun. It's conceptually quite simple. And while the planet passed in front of the Sun became a bit dimmer as seen from Earth. Well, similarly for exoplanets. So we do that here. You have here a star, the planet. You see the planet passes in front of the star, and you see here this sort of dimming of the star, which will be about 1% for a typical Jupiter-sized planet on a typical Sun-like star. Now, what's interesting is that this method here will happen with a certain known probability. It's purely geometric. So if we put our star here and we put our planet there, any star that is within this cone here will see the planet in transit. So for instance, I put myself here, like along the line, I will see, looking at the star, will see the planet interrupting the star. Objects that are here don't see the star in front of the planet. And so this arc here is simply a probability. And you can see that if I move the planet a little further away, the angle here becomes a lot sharper, and therefore the probability shrinks very rapidly. And so for when people were trying to find planets, or thinking about finding planets, they were thinking, you know, like the planets would have periods of maybe 5 years, 10 years. They would be at, you know, like 3 AU, 10 AU, something like that. And at these distances, just the transit method just simply doesn't work. You don't want to do that. The probability of transit is tiny. And then you're looking at an event that would last 15 hours every 10 years. So to be observing it at the right time would be almost impossible. But as soon as hot Jupiters were detected, then people knew that the probability was high. And you can see probability for a hot Jupiter is typically 10%. And you can see that it plummets very rapidly. So this is very high. And it means that if you observe enough stars, then you will detect planets through that method. And potentially what you can do, so with spectrographs, what you do is that you only look at one star at a time. And then you measure velocities over, you know, several weeks. And then you find out which one have planets. The advantage of the transit method is that you can observe at thousands of stars at the same time, which allows for rapid detection of exoplanets. Then the signal that we detect for the transit, so it's typically 1% for a hot Jupiter around a sun-like star. But if your hot Jupiter is twice the size of Jupiter, then it's 4%. And then if your star is a bit smaller, it can be also 4%. So we're looking at signals between 0.2 and 4% in transit depth. And that's where transit surveys come in. So the wide angle search for planets is a British project that I worked on during my PhD. So I don't know if when you were prospecting universities, if you went to the universities of Kiel or St. Andrews, Leicester, and Warwick. So several of these universities decided to operate the Wasp experiment. So there are two observatories, one in the Canary Islands and one in South Africa. And you see 8 zoom lens here. Those were bought on eBay. The primary reason is that they had ceased construction, and they were also cheaper that way. And on the back of them, there is a scientific CCD detector, a very sensitive detector, more sensitive than the telescope in the Lickey Hills. And that's typically, you know, like what we see. So you see that it's not great quality, or at least it doesn't look great quality. This is a comet, by the way, that was just happened to pass in a field of view. It's not very good quality, but they're very good at recording light. And then Wasp was scanning the sky, and every night we could do 10% of the night sky. And over several years, so now the numbers are a bit out of, I don't know now what the numbers are. I've left the experiment for a while, but at least for about 10 years, we observed 30 million stars, 20 to 30,000 times each. So an insane amount of measurements. And you see the map here tells you, like the color tells you the density of measurements that we have on certain stars. And you can see here the 8 cameras of the southern experiment, and here you would see the 8 cameras of the northern telescope. And so we measure the brightness of stars with those and try to find for periodic signals that will look like transiting planets. And then what we do is that because there are many things that could mimic a transiting planet, then we need to confirm it with the mass, with radial velocity. So instead of starting with radial velocity, we start with with photometry, and then we do radial velocity to measure mass. So this is the Swiss telescope at La Silla. It's a small telescope, only 1.2 meter in diameter. It's a modest size, but it's a very beautiful machine. And I don't know if you will hear sound from this. Let's see. Record and cloud. I wonder if on the video. Let's see. No, there is no sound yet. So do you hear sound now? That's like the control room of the Swiss telescope, and I wonder what your image of working astronomers is, but it can look like this.
We can hear that.
So I hope now you have a less serious opinion of us. At the time, certainly as grad students, we were having a lot of fun. I spent more than a year living in that place, all combined, observing stars. And these were three of my friends, actually, who did this very funny sort of Harlem Shake at the time when this was a viral thing to do. So here are the data that we typically collect on such a system. So what you see here is the Wasp data. So you see it's not very precise. There is a scatter here of about 2% in amplitude. But because we observe thousands of times, then the transit is fairly clear. As you can see here, there's a little something going down. These are better light curves. So Luke mentioned TRAPPIST-1. TRAPPIST-1 was observed by the TRAPPIST telescope, which is at the same site. And you see here light curves made by that small telescope, and which show that confirm the transit in various bands. And here you see those radial velocities that confirm the mass. And so when everything is fit together, you can get a pretty good constraint on your planet. Wasp was the most successful experiment for finding exoplanets before Kepler, a NASA satellite, was launched. NASA spent $1 billion to do it. With Wasp, we only put what, 100,000 pounds to make it. And until the second year of Kepler's launch, we were still the most effective team in finding planets, the most efficient in terms of number of planets detected per year. And you can see now there's a few more planets, but at the time I left, we discovered more than 100 planets just in the southern hemisphere where I was in charge. And there are two reasons for that, why we found so many is one, because we had both the photometry and the radial velocity in the same team, whereas other teams like HAT, for instance, were doing the photometry, but they were reliant on others to do the radial velocities. And also because we were the only ones in the southern hemisphere. So that meant that we had a lot of competition in the north, but almost none in the south. So it's a bit easier to carve a monopoly that way. So here is something to show you why we need those radial velocities. So you see here a graph showing masses in units of the Earth, and here in units of the Sun. So the Earth is here as 1, 1, mass of 1, radius of 1. And here you have the solar units, and the Sun is here. So 1 and 1 here. So you see stars are very well defined. And then you arrive into the planets, and suddenly it's very messy. And the reason is not because we are not doing our job properly. All those are very precise measured radii and masses. It's just that planets are a lot more diverse than stars are. So that was a bit of a surprise. We did not know that. You'll see later, I'll show a model, and the solar system is bang on the model. So it was a bit of a surprise that exoplanets were so diverse. You can see that typically the range that Wasp considers a planet to be is in this range. Oops, I clicked intempestively. Okay, it's typically in that range. The biggest planet is this one, Wasp 17. It's twice the radius of Jupiter. And within the band, so here planets below the dark area would be too small for us to detect, and above that almost certainly be stars. But you can see that from here to here you have the same size, and then you cover 1, 2, 3.5 orders of magnitude. And that's why we need the mass, because if you detect an object which is 1 Jovian radius, it could be anywhere along that line. So you have absolutely no idea. And that's why the HotJupiters are also sort of fascinating, I think, is that they have the same size as brown dwarfs and small stars, but they're planets. It's kind of fun. So what do you do once you have discovered all of these planets? Well, the first thing that we do is some orbital characterization. And why we want to do that is because we want to find out how HotJupiters form. And the main idea is that you have the star, the planet forms beyond the ice line, so like people thought to begin with, and then the planet moves in, it moves closer. How it does that, we don't know. And that was the big question at the time. Maybe it does it by exchanging angular momentum with a disk. So the disk is moving outwards, so the planet needs to move in by reaction. Or maybe the planets are formed together, several planets, and then they interact. And then one planet is placed on a very eccentric orbit, and then it goes right to the center of the system. and then tides will do the rest. And then I'll talk a bit about that. And so these two methods, this is a simplified way of looking at it, but these two methods were predicting two very similar planets, but for one observable. So if the planets migrate within the disk, you would expect the planets to remain within the plane of the disk and along the equator of the star. However, if the planets were interacting, they would go out of the plane and then be on orbits that are inclined with respect to the equator of the star. And so you would expect a mutual inclination between planets, but also an inclination between the equator of the star, where the disk used to be, and the orbit of the planet. And the only way to measure that at the time was what we call the Rossetto-Mclaughlin effect. So this effect is if your star rotates, then you will have a little bit that will be blue shifted, the part that comes towards you, and then this is red shifted, the part that goes away from you. Very much the same way as the radial velocity. And if your planet covers the blue shifted side of the star, then in average, your star will look redder because you're missing blue light. And so in your radial velocity, you will see a missing, an anomalous blue shift. And then as you go down, you will see an anomalous, an anomalous red shift and then an anomalous blue shift. And by counting how much time you spend on the blue side compared to the red side, like you can see, you can measure the angle of your planet. This is the lambda. It's also called beta by some people, like me, for instance. And so to do these measurements, we turn to another telescope, which is also in La Silla. You can actually go on Google Earth in La Silla. So if you type Observatory La Silla in Chile, go on it, and then you can just meander about and try and see what the telescopes look like. I really encourage you. It's a nice site. So one of the most beautiful observatory I've been at. And in that dome here, there's a 3.6 meter telescope with a HARPS spectrograph. And just to give you an idea, this is a person here. So this is really a massive telescope, and it's about as big a telescope as one could do in an equatorial mount at the time. Because of the equatorial mount, the dome is enormous. And in fact, now new telescopes are built very differently. They're built on what we call an alt-azimuthal mount. So instead of moving along the equator like this, they will have like a sort of two axes, left, right, and up, down in a way, which makes it harder to track stars. But it's easier because here it creates a lot of flexure for the equipment, so it makes it difficult to construct. And then the dome is enormous because everything needs to rotate within it. Whereas now with the alt-azimuthal, you can rotate the dome at the same time as the telescope. And it means that a telescope with alt-azimuthal and the same size as a dome, which is 3 times smaller. So a lot cheaper. And the dome is the half of the price of a telescope like this. To give you an idea, this dome is actually 500 tons. And to rotate, there is a rail track around it. And they had to change it once because it was completely used to the bone because of the pressure of the dome rotating every night constantly. So what does the Rossetto effect looks like? Well, it looks like that. So these are measurements. You see here a planet that is coplanar, so it goes along the blue side and then the red side. And here you see one that is retrograde, so it goes the opposite way. So like the star is rotating this way and the planet goes the other way, which is kind of weird. So how does that work? So the idea of tidal migration is one that I think for the HotJupiters works. For this planet, probably doesn't work. So this is probably disk-driven migration or maybe local formation. So planets could form maybe at this location here. For these guys, there's just not enough material to form a planet there. So either they disk migrated or they did eccentricity migration. But because you see there is a sort of overdensity here, it looks like a very special place. And the reason why it is a special place is because of tidal friction. So if you have a planet that comes right here at periastron, so at the closest to the star, just above this line here would be the Roche limit. So if the planet were within that, it would get destroyed. So if you're just there, then tidal migration will naturally, and again, if you come to my year 3, year 4, you will derive this. You will find out why the planet goes at twice the periastron distance. And that's because of angular momentum being conserved, but energy not being conserved in that system. orbital energy. And so you end up at twice the perihelion that you were at. And it turns out that it's exactly where we find the hot Jupiters. And so that was already kind of a good clue that dynamical interactions that happened. So I'll move a little forward, I think. And you can actually see that in the warm Jupiters, so the planets that have 10 days and above in orbital period. You can see here a zoom. So here, instead of mass, it's radius. It's effectively the same plot I showed before. We see the hot Jupiters here that are in Kepler. And each of the red dots here is a warm Jupiter. So they have periods greater than 10 days. And you can see that half of the dots beyond 10 days have other dots in the same system. And all of those are linked by lines, whereas none of those have other planets in the system. So clearly, the hot Jupiters here are very different from the warm Jupiters. And so although we still don't know how those formed, certainly these two populations are different. And that's also a sign, likely, that the hot Jupiters formed in a very special way in tidal migration, or like this sort of a very dynamic event between several planets, and then a very eccentric orbit is quite likely in my mind. And now there's a big push to understand those warm Jupiters better. And that's something that we do also at Birmingham. So now I'd like to share a little bit of atmospheric physics, or things that happen in hot Jupiters that are weird, just to encourage you to study this population. And I say that now hot Jupiters are seen as a bit old or passé in exoplanets, because people are doing super Earth, sub-Neptunes, Earth-like planets, all sorts of weird planets, young planets, all sorts of things. But in fact, hot Jupiters still remain very, very important type of planets. And there's much to learn from them. They're very special. And so like this is a weird planet, Wasp 12. Here you see it as a period of 1 day, the mass of 50% larger than Jupiter, a radius 85% greater than Jupiter as well. So it's sort of interesting. And here you see the temperature is 2600 Kelvin, the equilibrium temperature on the day side of the planet. And coincidentally, because luminosity is the radius squared and the temperature to the 4th power, this planet on this day side emits more light than, for instance, some stars like TRAPPIST-1, which has a temperature a little weaker than that, and is certainly smaller than this. One thing that we can that is interesting about these is because these Jupiters are hot. Water is in a form of vapor. So if you're trying to detect water on Jupiter, it's in the form of ice in clouds that we don't see. And when the Galileo probe that went around Jupiter was sent into the atmosphere of Jupiter after its mission, in order to kill the probe to avoid it crashing on Europa, which is a potential site for life in the solar system, and the probe was sent to be destroyed in Jupiter, but at the same time it sent back data. And although we sent a probe in the atmosphere of Jupiter, we still don't really know how much water there is in Jupiter. And although we can measure, water is H2O, so hydrogen and oxygen, we measure oxygen very well. We don't know how much oxygen there is in Jupiter. Whereas for hot Jupiters, all the water is in vapor form, so we can measure it. And so it's actually easier to detect water on a hot Jupiter, like thousands of light years away, than to do it on Jupiter in our own solar system. And that's where exoplanets are very, very useful. So one thing is that the planets are inflated. So we know that. You see that Jupiter, Saturn, Uranus, Neptune, Earth, and Venus are just there. In fact, actually, if I put models in there, you see here a model that we would expect for Jupiter and Saturn, and exactly on the model. And you can see that the planets don't follow that. It's very strange. And this is the radius inflation problem. It's still not solved. So after 25 years or 20 years now of knowing about it, we still don't know why this is hot Jupiters are inflated. We know it has to do with how close to the star they are. So the closer they are, the more inflation they have, but there's a big difference between the planets. And it ranges from different things, from internal heat, remnant from, for instance, when the planet was circularizing during the migration, as they changed from an eccentric to a circular orbit, to other things like ohmic dissipation. So this is rather cool. Effectively, what happens is that you have the star is ionizing the top of a layer of the atmosphere, and because you have ionized matter which is moving, because the day side is hot and the night side is cold, so it's moving, so it's creating an electric current. And creating an electric current, it induces a magnetic field, and through that, it actually helps inflate the atmosphere. There's really some cool stuff and cool physics to investigate. And it's still not known exactly whether this is the right process to inflate a gas giant, but it's certainly one of the main contenders. Let me see where I'm going. I don't want to. So, like, yeah, if your thing is not observing, but more like modeling, I encourage you. There's a lot of modeling to be happening on exoplanets, and this is one problem which is still not being solved. That I would personally like to understand at some point. So another thing that we do is atmospheric characterization, and that's also something that we can learn about a bit better in the class if you come. But it effectively happens when we are at transit or when we are at secondary eclipse right there. So when the planet goes in front of the star, when it goes right behind it. And the main reason that this happens is because of a lunar eclipse. So if you've seen my lecture on TRAPPIST-1, I will explain that already. But if you have the sun, the earth, and the moon in exactly this configuration, and the only light that reaches the moon is sunlight that went through the atmosphere of the earth, and sunlight here reaches the atmosphere. Particles within the atmosphere of the earth scatter blue light, meaning that it's a blue sky at midday. Maybe not in England, but elsewhere in the world, I assure you it's blue sky. And on the side of the earth, so sunrise and sunset, there's no blue light left because it has all been scattered at midday. And then you only have red light. And so this is when you see a lunar eclipse, I think what you're looking at are all the sunrises and sunsets of the earth, which I think is quite a poetic way of looking at it. And if you were on the moon, then it would look like this. So this is a series of pictures, which is sort of nice. Like it's an Earthrise from the moon by a Japanese probe by JAXA, the Japanese Space Agency. And you see the Earth rising above the surface of the moon. And the moon is dark because you're coming from the dark side of the moon. And you see here, the ring here is just our Earth, which is rather remarkable. It's a beautiful image of a total eclipse of the sun by the Earth. So if you place a spectrograph on this, you can get a spectrum. You can see here wavelength, bluer wavelength, redder wavelength, no light, lots of light, and you can see there's not much light here in the blue wavelength, lots of light in the red, and the picture kind of confirms that. And you can see that from this you can detect various things: oxygen, water. You see here various oxygen as the atoms bash into each other, and here is also a broad line of ozone. And you can even detect here is an oxide of nitrogen, which is a pollutant that you would find in the city. That's actually the main particulate that is of concern in the UK, where now cities are a bit too polluted. So you can see you can find quite a lot of things in there. So, the previous thing was sunset is often enjoyed, with a cocktail on the beach or something, and has a fairly romantic signal. For exoplanets, this is our signal, our life and death in a way. And the issue is, if you're trying to find a signal here, I encourage you to try to find it, but I'm not sure you're going to notice it. Finding a signal on Venus during an eclipse, during a transit, is very difficult in a direct way. And so we had to figure out some other method to do it. And that's what we call transmission spectroscopy, which I'll explain in a nutshell. That's the method that is the most productive at studying the atmospheres of hot Jupiters, and now we're deploying it on Earth-like planets. So if you have your star here and you have your planet right there, and your planet transits, so some of the stellar rays are intercepted by the planet, and you measure the size. Now, if you place an atmosphere that scatters blue light, the bluer wavelengths are stopped by the atmosphere, so you measure an apparent size here in blue. And then the radar wavelength, like during a lunar eclipse, go right through the atmosphere. And so you measure a slightly smaller size for the planet. And so by measuring carefully planet size as a function of wavelength, you can do some atmospheric work. And in fact, that's what these data show, or what they try to show you. So you have here the radius of the planet over the radius of the star squared, so the transit depth. So the size of the planet Here are the measurements. So you see the size here looks very flat. You see the same thing here as a function of wavelength. And you see the model. So here the planet would be bigger, and then it would be smaller, and then it would be bigger. And so it means that there would be an absorbent according to this model at this location and this location. But we don't see that. And the only thing we see is a flat line. And what we now know and didn't expect is that all of those are just clouds. Clouds, for the once, it was not cloudy on Earth when we tried to do these measurements, but then it was cloudy on that exoplanet. So we doomed clouds everywhere. And I'm sure you as members of Astrosoccer understand the frustration that you can have with clouds. And most of the exoplanets are cloudy, and that's kind of sad, unfortunately. Fortunately, a few of them have clear atmospheres, but it's a bit of a guess as to why some of them have clouds and others don't. Or most of them have clouds. And so that means that, and that's the reason for that is because we're observing just at the limb of the planet, the sunset and sunrise. And so if there's a little bit of opacity, like imagine that you have your planet surface here, then the rays are going tangential. And so if there's a little bit of opacity on the atmosphere, then the sun rays are being blocked very effectively. And so transmission spectroscopy suffers from clouds. So the other way to do that is to look at emission when the planet goes behind the star. And that's similar to what happens during the Earth's shine. So you see here, this is the dark, the moon, the new moon, and here you see the first crescent that is appearing. And the reason it's not completely dark is because you have sunlight bouncing off the Earth, bouncing off the dark side of the moon and into the night of the Earth. And so you observe that. And then if you put a spectrograph on this, you can see a reflected spectrum of the Earth. It's actually a very beautiful idea because it means that from the night side, you actually get an image of the day side. It's another poetic moment. So when you see that, it's effectively you're looking at people on the beach on the other side of the Earth. And what you see here is the same spectrograph. So you have a lot of light in the blue and not much light in the red. So again, what we're seeing is the day side. The Earth has a blue sky. So just from this data, you would deduce that. And you detect all sorts of molecules, which is very interesting. And these are the kind of measurements, I won't go into detail, that you can do. They're much harder to do. But the advantage is you only go through one layer of the atmosphere. So you're less, you're sensitive to clouds, but not as much as through transmission, where in transmission, you're going through an air mass of like 20 or something like that, whereas here it's an air mass of 1 for those that use the telescope. So I see time is running. I don't want to tie you too much. I think the last thing that I'll go through is the fun bit, I think, that we can do with exoplanets is trying to map. And I think first maps will be done on exoplanets. Will be on HotJupiters. In fact, the first has been done, but soon we're about to do many more. And so in a few years, I think you should have someone to come talk about maps of exoplanets. So what's interesting is that on this graph here, as you see, there's a transit, there's a secondary eclipse, but there's also a sort of curve that rises here. You see, if I have my dashed line here, it goes to the bottom here. If you have the second dashed line here, it goes here. And there's another top dashed line here, and that's because the light somehow increases. And it increases because you see the crescent here of the planet, waxing and waning, just like the moon. And these are data on the planet. So that's what it looks like effectively. You have the transit here. And then you have the minimum. So here is the darkest side of the planet. Here's the brightest side of the planet. And here the planet goes behind the star. So that's the stellar flux. And you can see that here there was a contribution from the night side of the planet that we wouldn't, if we didn't have the full phase curve, we wouldn't know. We would think that all of this is the transit depth, but in fact, there was a contribution here, which is due to the night side of the planet. And so if you measure the light here and the light here, what you see here is a difference between the temperature on the day side and temperature on the night side, because this is flux. It's again, radius squared times temperature to the 4th power. The radius of the planet doesn't change, so the only thing that can change is temperature. And then, so with this, you can do a sort of map like that. And what you find out is that it's actually hotter at tea time, like it is everywhere on Earth, and not at midday. And the reason that is because of wind. So that was the first evidence that there was wind moving the sort of material that has been heated at midday into the west side of the planet, and so wind is pushing this. So this is the kind of things that we will be able to do fairly soon. So this is far like more detailed, but what you have is that the planet goes behind the star, and so the star cuts the planet progressively in one direction. And when the planet exits the star, it cuts it in another way. So if you measure the ingress part of the trend of the eclipse and the egress part, so how fast the planet disappears behind the star and how fast it reappears, you have a sort of latitude and a longitude that you can mix together and create a map. And I realize now I forgot to insert a slide about the first exoplanet map. But effectively, it looks like the one I just showed you because the planet turned out to be fairly homogeneous. But that's that would be it. I think now I'll take questions if people are, can ask questions. I'm not sure how you're gonna make this work out.
I would just like to say a massive thank you, Anne-Marie. That was, truly a fascinating talk. I mean, I'm doing my my fourth year work actually with Anne-Marie on some exoplanet stuff. But this really blew me away. Really great talk. Thank you very much.
Thank you. Look, so if there are questions, I guess people can put them in a Q&A, or I don't know if they will be out. Anwesha, please.
I was just wondering, why doesn't our solar system have a hot Jupiter?
Well, on the face of it, there is 1 chance in 200. Okay, so we may have been the 199 lucky not to have one. So that's just assuming random, like independent probabilities. But if hot Jupiters form via very eccentric orbit and then tidal migration, then I think it would have disrupted any other planet within the system, and that's why we see them all alone. So the main reason behind this graph, for instance, and the reason why we don't see any companions to these hot Jupiters is because they destabilized every orbit on the way in, so to speak. And so the very reason that we have an Earth on which we can observe the sky means that there couldn't have been a hot Jupiter, otherwise we would have been expulsed and not exist.
Thank you.
I have another very brief question. So on one of your slides, you highlighted the similarities and the differences between both hot Jupiter or Jupiter-class planets, brown dwarfs, and stars. Is there, could you explain to us just how they're differentiated between?
Yeah, so at the moment we don't really know. It's one big debate as well, something that if you're interested as a student to work on, it's something that certainly will attract attention just because of the controversial nature of the work. But we don't know how massive a planet is until it ceases to be a planet. And we don't know how. So we know this location here. So stars fuse hydrogen to make it into first helium and then the carbon cycle and everything. And after a certain size here, so the smaller the star, or the less mass there is, at some point there is not enough mass, and what happens is that the density doesn't increase the center. What happens is that you have what we call electron degeneracy pressure. So just things are just floating around the same way that you can't go through your table because of EM forces. The same happens in a star, and so you can't increase the density, you can't increase the heat at the center. And so it means that hydrogen fusion no longer exists. And so that's where brown dwarf starts. And so that is a pretty nice limit. However, what we see if we do a histogram, so if I were, I'll draw on this. But if we were to make a histogram, let's see, can you allow me to annotate? Is there a way to allow me to do that? No.
Just have a quick look.
Let's see, no. Not there, what's that? No, okay, I don't see it. So yeah, like if you were to do a histogram of planets, then brown dwarfs, and then stars around, in binary systems, then you would see a gap there. There was almost no brown dwarfs orbiting sun-like stars, and that's a bit weird. So this limit here is about 80 Jupiter mass, or about 7% of the stellar mass. So it's not, it's fairly low. Here, so the brown dwarfs are defined by deuterium fusion. So deuterium is an isotope of hydrogen. It has 1 or 2 neutrons as well as the proton in the center. And for some reason, like this fuses at lower temperatures. So those brown dwarfs are fusing deuterium at the beginning, certainly, and after a while they stop. In fact, because they're not really sustained by fusion, brown dwarfs constantly cool and shrink over time. And the separation between planets and brown dwarfs is a bit uncertain. People say that deuterium fusion stops at 13 times the mass of Jupiter. But then if you were to draw the number, so if you take all sun-like stars and then you do a histogram of whatever objects are around them, and you do a histogram, it would look like there are planets, then there's almost no brown dwarfs, and then there are stars in terms of histograms. And the middle of this is about 25 Jupiter mass. And so it looks like there's no difference in the number of planets between, there's no difference in the distribution. It looks smooth between about 10% of a Jupiter mass to 25 Jupiter mass. It looks like one Gaussian. And then if you go from 25 Jupiter mass to, I don't know, something like a 0.2, 0.3 solar mass, then you see a log normal very, very naturally. So it's weird. So a lot of people place the sort of planetary mass regime at below 25 Jupiter mass. Some people say a brown dwarf forms from collapse, so like a star, and the planet forms within a disk. But again, there it's not completely known why, because it looks like some stars could form in disks as well. So that throws again there, and that's why there's controversy. And so in fact, one could say that there are deuterium burning planets, and there might have been core accretion brown dwarfs. I mean, some models even imply there might be a Jupiter mass of rocks at the center of certain brown dwarfs. Imagine that.
Wow. Yeah, that's
300 Earth masses of rock. Yeah.
No, that's excellent. Thank you.
I've got one more question.
Fire away.
This is more of a speculative question, given that I'm not an astrophysics student, but if there's a hot Jupiter, let's say, orbiting in a region where there are other planets, so we know that the hot Jupiter would it would perturb the orbits of the other planets and possibly even, maybe in a way disintegrate the other planets and take its mass, like the other planets' masses. Would there be then a possibility that by absorbing this mass from the other planets and the other gas close to its host star, that the hot Jupiter gets massive and hot enough to have fusion occurring and turn into a star?
Wow. Well, in a way, yes, but practically, I doubt it, because it would need to acquire 100 other Jupiter mass planets and not lose any of the other, material, gas or rocks and everything, but mostly gas. So I think that's where I think it would be quite difficult. It turns out, I mean, if you go back to the first plot, it turns out that the hot Jupiter is actually a little bit undermassive compared to the outer Jupiters here. And that's confirmed. And the reason is because probably it's easier to destabilize a lighter planet than a heavier planet. So, but maybe those objects, which are almost 20 Jupiter mass, those are brown dwarfs. I have been wondering whether those are planets that may have coalesced together. It's weird, but there's nothing yet. There's no way of proving that at the moment.
Thank you so much.
Sure.
Well, I must admit, I'm pretty out of questions, I think, for now. I will probably end up rewatching this talk myself. There's a huge amount of information contained in there, so thank you once again. It looks like we don't seem to have any other questions. I appreciate with it coming towards the end of term, it's a bit of a busy crunch time for everybody else. But luckily, we obviously have the recording of the talk, so people can go back and have a look when they wish. Very much like to extend AstroSoc's thank yous once again to you, Professor. and to wish everybody, yeah, you know, hope everyone stays safe and enjoys the last Astrosoc event next Thursday, which is going to be our annual Christmas quiz. Thank you to everybody.
Yeah, thank you, everyone.